about the modular forms. Modular forms. Yeah. Yes. So according to my ChatGPT, that modular forms is something related to the symmetry. In biology, you study the symmetry in space like this, asymmetry. This, and it seems that it is very different from that kind of the symmetry in space. So please tell us about what is modular forms. Thank you.
Yeah, thank you for your introduction. Nice to meet you. I am Yuya Murakami, and I joined iTHEMS in last October. So I'm a mathematician, and I studied about number theory, in particular modular forms. And I also studied the relation between number theory and topology via modular forms. So modular forms are the most favorite topic. So today I would like to introduce modular forms. So let's start. What are modular forms? Modular forms are rich objects in number theory. This is one answer. And the second answer is modular forms are effective tools for many areas. For example, physics, representation theory, and topology. So this is an overview, conceptual diagram of modular forms around many areas. So modular forms are object of number theory, and this is their application to Fermat's last theorem. Fermat's last theorems are proved by Wiles by using modular forms, and in his proof, modular forms appears in Shimura-Taniyama conjecture, which states that relation between modular forms and elliptic forms. And such such theorem is generalized to Lagrange program. And modular forms also relates to mathematical physics. For example, conformal field theory and topological quantum field theory, and so on. And modular forms also relates to representation theory. So for example, vertex operator algebra and moonshine phenomena, monstrous moonshine, is a relation to modular forms. And in recent, modular forms also relates to topology. This is wonderful. So in fact, quantum invariance, this is an object of topology and mathematical physics. Quantum invariance are related to modular forms. So modular forms are around many areas. Modular forms are everywhere. That is the gift one. Okay, so let's discuss the definition of modular forms. And Q, this is a power series in Q, is a modular forms of weight K. K is a non-negative integer. If FQ has the following kind of symmetry, that is, FQ, we consider Q equals to exponential 2 pi I tau for some complex number tau. Then FQ can be considered as a function of tau. Then we can replace tau as 1 minus over tau. Then this function is equal to tau to the k times FQ. Well, this is the definition of modular forms. But we cannot understand why modular forms are so important from this definition. But mysteriously, these modular forms have many applications to number theory, mathematical physics, representation theory, and topology. Okay. So today I'll introduce two applications in elementary number theory. Okay. The first one is Euler's pentagon number theorem. We consider an infinite product like this: 1 minus q times 1 minus q squared dots 1 minus q to the n dots. So we can expand this infinite product in by in hand. For example, we choose n as 100, and there are 100 terms, and we calculate this. Then, up to q to the 100, the first 100 term is like this. So we can also, using computer program, we can calculate easily this expansion. Then, mysteriously, this infinite product has a following expansion: 1 minus q squared plus q to the 5 plus q to the 7 minus, and the general term is 1 minus 1 to the n times q to the some number plus minus 1 to the n times q to the m times 3n plus 1 over 2. This is called pentagon number. So that's the reason why this equality is called pentagon numbers. Okay, so in general, such a product has large coefficient, but this theorem suggests that this infinite product only have the coefficient plus minus 1. This is amazing. Okay, so and this equality is elementary, but the proof is very difficult. In fact, Euler's at first Euler's discovered this equality by in hand, and he gave a proof after 20 years. So that's very difficult. But modular forms provide a proof, a simple proof of this equality. Okay. So in the proof, the first step, we consider q times the left-hand side to the 12, and q times right-hand side to the 12. Then, mysteriously, this is a modular form. In fact, this is a modular form of weight 12, and a0 equals to 0. Here, a0 is the first coefficient in power series. Okay. So in the second part, we can prove that this vector space, this forms a vector space because this condition is contained by scalar multiplication and additive. So this is a vector space over C, and we can prove that this vector space has dimension 1. So in the dimension 1 vector space, we have 2 elements. So these 2 elements are linearly dependent. Thus, we have some constant C such that q times the left-hand side to the 12 equals to q to the right-hand side to the 12. And so we have some constant C prime such that left-hand side equals to C prime times right-hand side. And by comparing constant term 1 and 1, we have C prime equals to 1. That is a proof. Okay, so I discuss about in the detail of in the step 1 and step 2. In the step 1, this is some technical part. So left-hand side can be written as dedicated function. So this is an element of S12. And the right-hand side can be written in terms of theta functions. So this is an element of S12. And in the second step, the dimension formula is proved by considering Riemann-Roch theorem for the modular curve. This is a special type of Riemann surface, SL2Z over some complex upper half plane. Yes, but this is technical, so I omit the detail. Okay, so this is the first application of modular forms. I want to give a second application, that is Lagrange or Jacobi's four-square theorem. for any non-negative integer n, there exists non-negative integer a, b, c, d such that n equals to a square plus b square plus c square plus d square. So any integer, any positive integer can be written as a sum of 4 squares. Oh, this is interesting. So I give an example. 7 can be written as 2 to the 2 square plus 1 square plus 1 square plus 1 square. And 8 can be written as 2 square plus 2 square plus 0 square plus 0 square. So 0 can be appears because we choose ABCD as a non-negative. And this type of equality holds for any positive integer. And so, for example, 196,884, this is a large number, but this has also such a decomposition. So in fact, this is really my favorite number. Yeah, because this is coefficient of some kind of modular form function. So important modular function, J function. It has a coefficient like this, and this coefficient is also related to a decimal representation of monster group. So this is very important grammar. Okay. So to prove this, we can also apply the theory of modular forms. So by the theory of modular forms, we can prove that this equality like this. So the sum of A, B, C, D non-negative integers of Q to this sum of 4 squares. Then this is equal to 1 plus 8 times the sum infinite sum, and to equal to 0 to the infinity of the sum of divisor d of n, which is not divided by 4 of d. So in fact, these left-hand side and right-hand side are both of them are modular forms of weight 2. And so by almost the same argument like this, you obtain that this equality. And here in the left-hand side, the coefficient of q to the n equals to the number of representation of like this, such representation appears in the coefficient of q to the n. And so such representation number equals to 8 times this part. And this part is positive because for any n, we have a divisor d as 1. So by this equality, we have the representation number is positive, that is this state. So by this is the power of modular forms. So finally, I'll discuss about more relation to mathematical physics and topology. Or I'll discuss about connection to TQFT, topological quantum field theory. So we consider within-list interactive invariant, WRT invariant, for 3 manifold n. This is a topological invariant of 3 manifold. Denoted as ZKM. Here K is a positive integer. And this complex number is defined as a path integral along like this. Here A runs a SU2 connection on M, and so this is a Chern-Simons functional of A. So this is a partition function of Chern-Simons theory. And so this is a physical definition, but we can also define WRT invariant in terms of mathematics, purely mathematics. And witness suggests that the reality invariant satisfies the following asymptotic expansion. ZKM has the asymptotic expansion as k goes to infinity as the main term, exponential 2 by I k theta times some power series. Here, theta is a Chern-Simons invariance of n. And Chern-Simons invariants are kind of topological invariant of n by defined by using the fundamental proof of. Okay. So this conjecture is widely involved. So how to prove this conjecture? So in fact, modular forms gives an answer of this. Zaghi and Garofaridis consider the following quantum modularity conjecture. For any three manifold M, there exists some map Zm from Q to the C to the R, which satisfies some condition like this. This is called quantum modular forms. This is an analog of modular forms, such that its value at 1 over k has a coefficient equals to zkm. This is a reality invariance, and so on. Then this conjecture, we can expect that this conjecture implies a asymptotic expansion conjecture. So that's why I studied about modular forms and quantum modular forms. So I'll stop here. Thank you very much.
Very much. So the first questions from the specialist, please. Yes.
So it seems that, if I understand correctly, the modular form, in both cases, you seem to be using the fact that the dimension of the space modular form over certain k is quite restricted.
Yes.
Is it the case in general? Do we know the dimension of any modular form space, and is there any infinite dimension one, or is it always finite?
Yes, always finite.
Okay.
And in fact, there are many variations of modular forms, but so for each variation of modular forms, such space is a finite dimension, and we have that dimension formula.
Okay.
Yes.
Yes.
Are there a few very important unsolved problems in the area of modular form?
One of the most important problem is Lagrange program. Yes, but this is not this Lagrange program is not purely for modular forms, but consider holomorphic form. This is a generalization of modular forms. So yeah, and for yes, so one of the most important thing.
The famous one.
Yes, very famous. And one of my favorite conjecture is Lemma's conjecture. Lemma's conjecture suggests that this part, in fact, the q times the left hand side to the 12 is known as Ramanujan's delta function, and Lemma's conjecture suggests that the Ramanujan delta, some behavior of coefficients of Ramanujan delta function. This is a widely known, and I think this is interesting.
One related question: is AI being used in studying the difficult questions in this area?
AI?
AI is.
I have no idea. Yeah.
So let's ask to AI. Yeah.
So I'm interested in the application too, because it has a very beautiful form. But I still want to ask you whether it has application, for example, in proving some another important theorem?
Yeah, well, one of the applications is famous last year. Yeah.
Was it used for Fermat's theorem? The application too was used in proving Fermat's last theorem. Yeah, application too.
Application two.
Yeah, I'm interested in.
Oh, this one.
Yeah.
So, I'm sorry. What is your question?
Whether application two can be
Application two.
useful for proving some other theorem.
Maybe this is interesting in itself. So I don't know.
I admit that it's interesting.
Yeah. So yeah. I have no idea.
Yes.
Thank you. I have a very naive question. So in your proof of the first application, it's not so immediate or to read why the power of 12 is important.
Yeah.
And also another question, why it's called pentagon on the theorem.
Why? Because this is called pentagon number. Because like this has 5 and 5 appears, and we consider like this. So then this is I think when we evaluate m as 3, then this is equals to the number of the points.
So the column can be always
Yes.
in the shape of the
Yes.
So then why 5?
Yeah. And power 12 is very mysterious. Yeah, very mysterious. But yeah, very mysterious. But I don't have any simple answer of this. Yeah, what to say, but sometimes in mathematics and physics, always 12 or 24 appears. That's a reason. Yeah, this is very important.
I mean, yeah, that's
Yeah.
outcomes.
That's yeah.
Application one. You said that the coefficients only plus minus 1 is very
Yes.
special.
Yes.
How about the inverse problem? Other than this, suppose you have the series with the coefficient plus minus 1, then in which situation you can put into the form of multiple systematic way in the like that series. I just want to know how extent the coefficients plus minus 1 is so special.
Yeah, I have no idea. So this example is very simple. So the only plus minus 1 appears, but in general, so such type of equality are very widely known, but most of them appears more complicated coefficient. Yeah. Let's say so. This is a kind of theta function. So and its coefficient can be considered as a representation number like this. So in this case, the representation number is simple. So only plus
Thank you.
yeah.
The application 2, why 4? Is it possible to reduce to 3?
No, this is an important point. Yeah. So yeah, four.
So
Actually, four times 3 we have 12. So yeah. So this is point. What to say? So yeah.
increase, you can allow the number. It is very easy. But if you reduce the number 4, or to 3, it becomes suddenly quite difficult. And the 4 is the minimum value which is possible. So,
Yes.
I want to know.
Yes, So the number 4 is appears naturally in the theory of modular forms. Yeah.
Sorry, I want to ask application 1. And the left-hand side has a lot of 0, right?
Yes.
On the complex unit circle, right?
Yes.
Are the coefficients and the power related to that 0?
So power.
Yeah, coefficients become -1 to the m, and the power is also given like that.
Yes.
And are they related to the position of 0 of the complex circle?
Yeah. In this case, I think no, but I introduce more interesting phenomena. So we consider the inverse of this. And then we have other expansion like this. This part we and in general the Pn yes, this Pn equals to the number of partition of it. So partition number. So and you suggest that this has many zeros around the unit circle, and we consider the 0 of unit circle of this. Then we obtain the closed formula of Pn. Such method is called circle method. So this is one of the application of modular form. Yeah. Thank you very much.
So in application 2, it seems non-trivial to, it seems non-trivial to find A, B, C, and D for a given non-negative number.
Yes.
Is there any program you can find systematically? But also, is it unique?
It's not. This ABCD is not unique, and generally, there are many ABCD because the number of ABCD equals to A times this number. Yes, and I have
For example, this 196,884 seems to be very long.
Yeah, this is chat GPT. I fully check in what to say, calculator. Yeah, but for example, we can consider the primary composition of n because this product form is stable under multiplication. Because this is a node of coternions. Yeah, so we can reduce to the case when n is prime. Yes, this is one of algorithm, I think. Yeah, but I don't know this is a most fast program. Thank you very much.
Excellent.
I have a very simple question. So this is a form of power series.
Yes.
And what is the form of power series which is not a modular form? I want to know what types of form of
yes.
cannot be a modular form.
In fact, I consider this power series as convergent series, and modular forms are very miracle objects. So the most Q series is not modular forms. So this is very miracle situation. Yeah, and there are two construction of modular forms. The one is theta function like this. Yeah, like this. And the second construction is due to Eisenstein series, like this. This two construction is famous to give modified forms.
Good. So the questions from the specialist, please. Yes.
So I really like the proof of condition one of this Euler's pentagonal number theorem. And it looks very natural to me if I interpret everything in terms of like, sections of vector bundles. So
Yes.
we have line bundles on portion of the vector space for the so fluid.
Yes.
Then you have the Riemann theorem chart and the dimension of this. And
Yes.
but one thing that isn't clear to me is how on earth would you have guessed that this sort of thing, like if you write this formula, I mean, you can check that this will satisfy the condition could be in modular form in section, but it's unclear to me how you could guess it if you.
Sorry.
So why would you guess that this left hand side to the power of 12 would be such a section from, I don't know, from the algebraic geometry? Does it have some interpretation? Some geometric interpretation?
So, in fact, this relation suggests that the FQ is a section of symmetric product of holomorphic manifold because the tau. So we consider the simple calculation. So we consider that the tau by considering this transformation, the tau equals to root square times the tau. Yes. So that's the reason. Yes, that's the reason. No. So this relation is equivalent to FQ times the tau symmetric square of K over 1/2 of K is invariant and tau to the -1 over tau. So that's the reason why the forms can be regarded as a section of line bundles.
Yeah, this I knew, but I wonder how you can see that as this section. Like,
This
at the right hand side, because it looks completely unrelated to any geometry. Like historically, did somebody just notice that this is the case? Or did it come from geometry?
I have no simple answer, but my answer is that the left hand side and right hand side are also can be written as the function and theta function, and by using some technique of Fourier transform or Poisson summation formula, we obtain this quality. And so we can consider section of the whole line bundles. Is it okay?
Yeah, cool.
I'm not a specialist, but may I ask a question? So it seems that this can be used for the various use.
Yes.
And here that form is very special. So are you obvious to me that to you that this can be found in various fields? Why you can find that form in that?
So why I
私このいろんな分野でこの形が見つかるんでしょうか。
that's mysterious. Very mysterious. I think I have no answer because this is one of the mystery of modular form. So, for example, in the mathematical physics, so modular forms naturally appears when we consider S transformation, S duality. Then modular forms appears. That is one reason. And the relation to representation theory is I'm not familiar with this, so I have no idea. And in the relation to topology is also this is also relates to SQLE. So that's why modular forms appears.
So will we find this in biology in the future?
I have no idea, but maybe in future the forms appears. For example, in computation theory, modular forms also appears because this type of symmetry can be so if Q is near to 1, then this series is not fast convergent. But by taking tau to the -1 over tau, then this Q has radius very small. So we can calculate this part fastly. So that's the reason why modular forms can be applied to the computation theory.
See? So any other questions from yes, please.
If I were to implement that application to very naively, I first impose the order that A is greater than B, greater or equal than B, and then try to first find the number that's maximal but lower than n, and take that as A. Let's subtract that square from n, and then try to find the maximal square from that difference, and then subtract that, and then try to find that polynomials. But does that work in one step, or do we have to search for other?
So you consider the program to
Yeah. So if I were to implement that at first, choose a candidate for A. So the easiest way would be to look for the maximal number that does not exceed n.
Yes, I think yes, I think yes.
Does that work in one step, or do you have to?
Yeah, I think many steps.
I think it's not that.
Yeah.
Because for that example, it seems like if you choose the maximal number for 1,
Yes,
and then you choose the maximal number for 9, and then the remaining one is like this.
But it's not guaranteed that 4 steps.
Yeah.
Is enough.
Yeah. So I think. So my question was whether that's that finishes in that single step, or we have to try more. I see.
Yeah.
Yes.
Yeah, we know that this four-square theorem has a generalization to so-called Morris problem.
Yes.
So for example, we can consider 9 cubic theorem or 17 fourth problem.
Yeah.
So in that case, what is the this generating function? Is it still a
all same like this?
so it's also modular?
No,
No.
that's the point. So we consider that 3 case.
Yeah.
Then this is not modular form in sense of this. In fact, this is a half integral range modular forms, but this is not.
So you can still talk about some modular problem.
Yeah, but I think in the application to the varying problem, modular forms are not so effective, but we need to consider. I think what to say. 外近質ベクトル空間、いや、prehomogeneous vector space. Prehomogeneous vector space is also is more useful rather than modular forms to apply varied programs.
Any other questions? So finally, may I ask that how this what you talk today, how is this related to your recent study?
My recent study is about this conjecture. So
I see.
yes.
Can I make one announcement because he's going to?
Yeah, yeah.
So today's speaker, Yuya Murakami, will be giving a math seminar on March 13th. So please attend if you're interested.
So thank you again for the Murakami-san.